So let's convolve a rectangle with a decaying exponential. And this happens to be the impulse response of a low pass filter. All right. And for this example, tau is going to equal RC is going to equal to 1. Now again, this tau is different from the dummy variable tau. Um, Unfortunately, all the teaching materials I see for integrating in time use tau as a dummy variable. Um, there is an alternative way of saying having RC is that I can have something called, oops, omega naught, which is 1 over RC. And then I could just have omega naught here and omega naught here, and then that might reduce the confusion. But to follow the book and anything you might see online, I kind of have to keep it like that. So anyway, I'm going to expand this out, and I get a step convolved with this decaying exponential and minus a step which is delayed times a decaying exponential. And really, there's only one convolution that needs to be calculated out, and that's this one, because then we can just scale it by -1 and delay it by 5. Okay. Now, mathematically, I'm just going to call this kind of intermediary function zt, right? And we'll integrate from -infinity up to t. And I have put the system response here as tau, and then done the t equals t minus tau substitution on the step function because it makes it easier. All right. So we just integrate through and we get 1 minus e to the minus t divided by RC. And in this example, RC is just going to be 1. Now, let's just do a quick intuitive plot. All right, here's my impulse response of a low pass filter, and the area is 1. All right, if I were just to, or approximately 1, if I was just to integrate this from 0 to 5 tau, I would get close to 1. And that'll help us determine what the maximum value is later. All right, so we have, like before, a time before there's overlap, a time when there's overlap is increasing, and then a time where it will flatten out. Now, this is kind of based on the assumption that after 5 tau, this function is effectively 0, right? And you can see that as time goes on, the increase in the summed area in time goes down. And so you could draw something like this. And this is just a rough sketch, but the important things are it takes 5 tau, and it goes up to 1, and it starts at 0, and it has some kind of exponential approach to it. All right. Now, how can I tell that that is 1? Well, this, like I said, this area is 1, right? So the overlap is between here, and that area is 1, multiplied by the step function, which happens to be 1. So you get 1. So let's now do the plot. So again, I've called that initial convolution z of t, and I've just written that down here. And then what's scaled and delayed, right? Minus z, and delay it by -5. Important to put the minus sign here, t minus 5, and divide it by the RC. All right? And then you have to make sure that it doesn't turn on until 5 seconds have gone by. All right? So the total function is z1 minus z minus z minus z minus z delayed by 5. All right, that's all written out. So we can break that up. Right, here's the step response of of a low pass filter, right? And that's in red. It's 0, and then we have exponential approach after 5 tau, and then it comes to 1. Now, the minus zt delayed by 5, right? So it's 0 until 5 tau, tau equaling 1 in this case, right? And it's inverted, so we get that same shape, but just inverted, and it reaches minus 1. And then we sum it, right? So there's nothing to, there's really only one function until 5 tau, right? And at that point, this is subtracting until we come right back down to 0. So that would be the plot. Now let's go. Now this animation took kind of a long time to calculate because the plot is it's generated with the convolution algorithm, which, as programmed, basically is integrating from here to here, then it goes back and integrates up. So to calculate the integral, it goes all the way back up and then just sums the next dt rather than saving whatever value it's at and just adding the next value. And this should be t. It's telling you what time this figure is at. Not quite sure why that popped up as F0, but again, it took a long time to calculate, and I got to move on. So now there is some overlap, and you can see that it's increasing, but then the increase is rolling off, right? And then at some point, right, it's just going to overlap completely, right? And if this wasn't a rectangle, it was just a step, it'd keep going. But now the other area is now being subtracted, right? And so the thing is this simulation, the red dot and all of that, is a numerical simulation, but this plot, right, is actually, we can calculate it. So really, it's much more efficient to calculate the response in this case than to numerically simulate it, especially with the algorithm being used. But this shape, right, this is exponential decay, but I could have kind of a triangle looking thing here, right, approximating that, and it would still kind of start at 0, go up to a value, and then come back down. Which you could call an Easter egg for some exam questions. So that's pretty much it for this. I think I might do, what one might be considered a really complicated convolution just to see how it all fits together. But that we'll see.